Welcome to chapter 13.4, where we're going to talk about curvature and the normal vector to a curve in space. So I want to begin by just getting some motivation for why we're going to be studying these. So in the last 3 chapters, we've talked a lot about curves, vector-valued functions, right? Curves in the form like this, r of t equals something. And those trace out curves in space where every value of t gives you a vector, and by connecting them, you trace out a curve in space like this. So this is just an example one. And some of the things we've learned about so far are the tangent vector. So one of the things we've seen is that by taking the derivative of the position function, right, the vector function, that will give us a vector at every point tangent to the curve. Right, so this might be the tangent vector that we call, sometimes we call that the velocity vector, which is equal to the first derivative of the position function. And then we talked about a special flavor of a tangent vector, which was the unit tangent vector. And the unit tangent was the direction vector, right, the velocity vector normalized, so it's just of length 1. And so we found those as well, and that might look like that, where that is of length 1. And so we would call that the unit tangent, and you remember the formula for that was the velocity vector, right, divided by its magnitude, so that it's equal to length 1. And so all of this has been talking about kind of the direction the curve is going at that point. Right, the tangent vector is always going to point in the direction of motion at that specific value of t. So now that we've covered direction, where the particle is heading, we're going to be talking about curvature, or we want to study in this section. So we're interested in how a curve now is turning. Right, and we'll call that, it's curvature. So you can imagine here, on this point of the curve, has less curvature, it's less curvy than maybe a point up here, right? This has much more extreme curvature in this localized area than this point down here. And so we have a value that quantifies curvature. And so when we're trying to define how a curve is turning through space, the first thing we'll look at is the curvature, and we call that kappa. So typically the symbol we use to denote curvature is this kappa letter. And kappa, the formula for it, is equal to 1 over the magnitude of velocity times the derivative of the unit tangent vector, right, times d tangent vector dt. So that is 1 over the magnitude of velocity, basically 1 over speed, times the magnitude of the derivative of the unit tangent vector. And why that works is, if I were to just draw an example curve over here, I'll make this like a 2D curve. So we'll call this some example position curve. If I have, let me pick this point. Actually, I think it'll be better if I make it a little bit more extreme. Let me make the curvature of this more extreme. Okay, if I pick this point here, and I just plot what its unit tangent vector would look like, it might look like this. And then if I pick another point a little bit farther along the curve, and plot its unit tangent vector, then we can kind of see that the change in the unit tangent vector is going to be equal to the change between these two vectors. Right? So if I draw these plotted from the same origin, you might have something that looks like this: unit tangent 1 and unit tangent 2. So plotting the change of them is actually going to give you this vector right here. So that is the change between those two vectors. And the more extreme the change is, the larger this value d tangent vector will get. So, at a point of less extreme curvature, maybe right here where the curve is not changing that much, this tangent vector and this unit tangent vector, they're almost going to be identical. The change between them is very small. So in this term here, for curvature, this value will be small. The change in unit tangent over the change in t. Where this right here, the change in t, this is, right, dt. And when you take the derivative, that change becomes infinitesimally small. So I'm drawing out an exaggerated version of what we're looking at here. But that's kind of the theory or the background behind why this formula works. And you could imagine for a straight line, when we plot r of t as a straight line, that would look like this. Then if I were to plot two different unit tangent vectors, you'd get one there. So there's two unit tangents. Then the change in this case in the unit tangent will actually be the zero vector. There's no change. And so if you were to plug that into this formula for a straight line, right? The change in the unit tangent vector over change in t on the curve is going to equal 0. So there's zero curvature on a line, and then the more the curve deviates from being a straight line, curvature will increase. So that's the idea behind curvature. And then there's another idea called the radius of curvature. And the radius of curvature is a value that is a radius. So the radius of curvature is a value that is a radius of a circle. So it's the radius of a circle that is tangent to a curve at a point, right, or a value of t. Let me write that better. And so the radius of curvature is going to look like this. Let me draw another example. So here's our example r of t. Let me just pick this point right here. So if we pick this point to be our value of t that we're evaluating at, you can imagine it would have a moderate amount of curvature, much more than this point over here. This is probably where the curvature would be maximized on this example curve, is somewhere in this region. The radius of curvature, and what we use to denote radius of curvature, is the Greek letter rho. So we call this rho, because it's lowercase r for radius. And so in this case, we're trying to plot a circle that is tangent to the curve. So the circle at that point of t is going to have the same curvature. So in this case, it might look something like that. Oops. Let me see if that'll turn. Oh, it was so bad, it didn't even correct it to a circle. There we go. So let's see, can I put it right there and then make it a little bigger? Okay, so this would be what we sometimes call the kissing circle. So the properties of the kissing circle is that it's tangent to the curve, and at the point that it meets the curve, it has the same local curvature. So the curvature here is equal. And this lowercase rho, the radius of curvature, is this radius right here. So it's the radius of this circle. We call that rho. And you can imagine at this point for t that the curvature is very low. It's nearing a straight line, so its kissing circle is going to be massive, right? Because it has to have the same local radius. It's probably even bigger than that, right? It's going to look something like, maybe something like that. So for a point on a more straight section, you're going to have a really, really big kissing circle because that radius of curvature right there has to be really small because the curve is so flat. So in this case, rho would look like this. And so you can imagine as t moves along the curve, you're going to have these different kissing circles with different radiuses of curvature. And you might be able to guess the relationship between curvature and the radius of the kissing circle at every point, right? We see that when curvature is higher, right, when you have larger curvature, we tend to have a smaller circle, kissing circle, right, with a smaller radius. And when our curvature is very low, right, small curvature, then the kissing circle has a very large radius. And so that relationship holds true. So the relationship between curvature and radius of kissing circle is this, right? We know that the radius of the kissing circle is inversely proportional to its curvature. So it's 1 over the curvature. And right, we can see how that holds true in this case. Okay, let's move on and talk about one other idea, and that's the unit normal vector. And that looks really similar to the unit tangent vector, and it's very, very closely related. So the unit normal vector, it might be helpful just to plot it on this curve and draw what it is. So let me come back to this example here. We found the unit tangent vector, and the unit tangent vector kind of tells us the direction the particle is going at any moment, so where the curve is heading. The unit normal vector, you can guess by its name, is a vector that is going to be normal to the unit tangent vector, so it's at a right angle, and the unit normal vector points in the direction that the curve is turning. So in this case, the curve is turning this way, to the left. So if I were to plot an example unit normal vector at this point, you would get a vector that looks like this. And the way we call the unit normal vector is capital N. And these are always going to be at right angles. And so the unit tangent vector points in the direction of motion, the unit normal vector points in the direction of curvature, the way it's turning. And here I can plot the same two vectors, right? The unit tangent vector is almost going to be coming kind of like towards us. And the unit normal vector is going to point in the direction it's turning, which in this case is to the right, coming towards us. So it'll look like that. And both of them are of length 1. So let me formalize some of this. So the unit normal vector is a unit vector that points in the direction the curve is turning. So this is also related to curvature. It's pointing in the direction that we're turning. And so the formula for finding it is actually pretty simple. So the unit normal vector is equal to the derivative of the unit tangent vector, right, dt, divided by its magnitude to make it a unit vector. Right, and that makes sense. It kind of follows the same idea we had up here, that you can even see in this case that the change in the unit tangent vectors, right, in this case, is going to be this difference vector, the change between the two. And if I were to just move, right, this change in unit tangent vector right here, the drawing's not perfect, but you can see that it shows the idea that these two are going to be orthogonal. The unit tangent vector is going to be orthogonal to the local change in the unit tangent vectors, right? And that would be, in this case, the unit normal vector. So let me just put that back where I had it. So another way you could write this is you could write it as capital T prime divided by the magnitude of capital T prime. So that's an easier way to write it. And then just for the sake of the clarity of the notes, I'll make another example curve here where we plot at this point a unit tangent vector and a unit normal vector. Points in the direction it's turning, always orthogonal to t. And you can see, if I can select all of this, let's see, how am I going to do this? And you can see that as t, the parameter t, increases and you move along this curve, then your t and n vectors are going to change. Can I rotate it? Yeah, here we go. So let me just do a little animation with my hands. So you can see that as we travel along the curve, as little t increases, these two vectors kind of act like this. They're always of length 1, and it's always pointing t in the direction of motion and in the direction it's turning. So this is where the iPad comes in handy for doing these manipulations. So they change as t increases. So let's try this out in an example. The example is asking us to find the unit tangent, the unit normal, and the curvature at lower kappa. How do I get this? Kappa for this curve where r of t is equal to e to the t cosine ti plus e to the t sine of tj plus 2k. So let's just start out by finding our unit tangent vector. So let's find this first. So if you remember, the formula for the unit tangent vector is equal to, right, the velocity vector over the magnitude of it. So let's first calculate the first derivative, v of t. So in this case, that'll be equal to e to the t cosine t minus e to the t sine t, all of that in the I direction. Right, and there I use the product rule, plus, and I'll do the same rule here, e to the t sine t plus e to the t cosine t in the j direction, and then the derivative of 2 is 0, so we have no k component in this case. Now let's get the magnitude of it. So the magnitude of v is going to be equal to the square root of e to the t cosine t minus e to the t sine t squared plus this term all of that squared, and now we can extend this like that. And what does that come out to be? So let me pull out the e to the t factors from each one. So we'll get the square root of e to the t squared, so e to the 2t. Oops, how do I do this? e to the 2t times, right, this will become 1, cosine squared plus sine squared. And then this term here will do the exact same thing. So I'll pull out the e to the t squared out front, leaving me with sine squared plus cosine squared is 1. So we get e to the 2t plus e to the 2t. And then we can simplify that down. That gives us, under the radical, we get 2 e to the 2t, which we can pull out the e to the t, right, times the square root of 2. Yes. Perfect. Okay, so that's the magnitude of the velocity vector. So now we can construct t. So t, right, the unit tangent vector, is going to be equal to this vector divided by e to the t square root of 2. So we can write that out. It's going to be, I'll put big parentheses. We'll get, this is going to work out nicely. Right, these e to the t coefficients are going to cancel out. They'll divide out with this e to the t down here. So we're only going to end up with the square root of 2 in the bottom. So I'll just cancel those out from the beginning and get cosine t minus sine t, all divided by the square root of 2 in the I direction, plus, same thing will happen for this term, sine to the t plus cosine t, all divided by square root of 2 in the j direction. So there we go. That is the unit tangent vector in general. So we could plug in any specific value of t and get a point on the curve, and then plugging in that specific value of t here would give us the unique unit tangent vector for that point. Let me switch colors here so it doesn't get confusing. Next we'll find, let's find n. So now we're going to find the unit normal vector, which you remember is t prime divided by the magnitude of t prime. So first we need to calculate the derivative of this guy. So the derivative of the unit tangent vector in this case is going to be negative sine t minus cosine t. Right, still all over the square root of 2 in the I direction, plus the derivative of sine is cosine t minus sine t, all over the square root of 2 in the j direction. Now let's get its magnitude. So we need to find, let me just make it more clear what we're doing here. Oops. All right, so here we're finding t prime. So now let's find its magnitude. So the magnitude of t prime is going to be each of these squared, added together, take its square root. So we'll get, negative sine t squared. I'll just leave out the squared, minus cosine t over square root of 2 squared plus cosine t minus, not that these signs are going to end up being important, all that squared, and then complete my square root hat. And that will give us, what does that end up giving us? So we get 1 sine squared plus cosine squared, 1 over 2 plus 1 over 2. So that gives us the square root of 1/2 plus 1/2, which is just 1. So conveniently, the magnitude of the unit tangent vector everywhere is just 1. Or the magnitude of the derivative of the unit tangent vector, excuse me. We always know the magnitude of the unit tangent vector itself is 1. We just found the magnitude of its derivative everywhere. So now, to construct the unit normal vector that points orthogonally, we just need to divide this by 1. So we end up just getting this. So because it's just that, I'll copy and paste it. Copy, paste. There we go. So we found the unit normal vector. And now let's find curvature. So find... I always write my K's a little funny. So we're finding curvature. So if you remember from up here, the formula for curvature is 1 over the magnitude of velocity times the magnitude of the derivative of the unit tangent vector, which conveniently we found all of these pieces. We know this and we know this. So 1 over this value. So we'll get 1 over e to the t square root of 2 times, right, it was times the magnitude of dt, which we have right here, right? That's the magnitude of the derivative of the unit tangent, which conveniently is just 1. So we get times 1, which ends up giving us 1 over e to the t square root of 2. That's the curvature at every value of t. Let me just box some of these so we know what we found. So we found t. We found n. And we found the curvature at every given point. So for all of these, we could plug in a specific value of t and then evaluate what the specific unit tangent, unit normal, and curvature is for every given value of t. And just for fun, it wasn't asked for in the question, but for fun, let's calculate what the radius of the kissing circle at every point would be. So for fun, calculate lowercase rho, or rho, right? And so rho is this idea here where we found curvature at every point, but now we want to know what the radius of the tangent kissing circle is at every point on the curve, and we can just use this formula here, that radius is inversely related to the curvature. So we know that rho is equal to 1 over kappa. So in this case, we'll get rho is just equal to e to the t square root of 2.